Differentiability over an interval. Hello everyone. To begin, let's reflect on what we have already covered. In the previous subsection, we focused our attention on the differentiability of a function at a single, specific point, which we denoted as c. However, when we move into practical applications of mathematics and physics, we are rarely concerned with just one isolated point. Instead, we are often interested in whether a function behaves smoothly over an entire range of values. This is precisely why the concept of differentiability over an interval becomes essential. In the upcoming slides, we will examine how to define and verify this smoothness across both open and closed intervals to ensure a function is well-behaved throughout a given set of values. 1. Differentiability in an open interval. Now that we have moved from discussing differentiability at a single point to looking at a range of values, let us begin with the concept of an open interval. An open interval, denoted by the parentheses a comma b, consists of all real numbers x, such that x is strictly greater than a and strictly less than b. It is important to note that this interval does not include the endpoints a and b. Moving to the formal definition, a function f is said to be differentiable on this open interval, from a to b, if it is differentiable at every single point x within that interval. To determine if a function meets this criteria, you must ensure that for every x in the interval, the derivative, which we write as f prime of x, exists and is finite. This is verified using the limit definition. The limit as h approaches 0 of the quantity f of x plus h minus f of x, all divided by h. Finally, keep in mind that this is a comprehensive requirement. If there is even one single point within the interval where the derivative does not exist, for instance, if the graph has a sharp corner or a discontinuity, then the function is not differentiable over that entire interval. Once we are comfortable with this open interval, we will move on to see how things change when we include the endpoints in a closed interval. 2. Differentiability in a closed interval. Now that we have covered open intervals, let us move on to the next case, differentiability in a closed interval. First, let us clarify the terminology. A closed interval, denoted as the interval from a to b inclusive, is different from the open interval we just discussed because it specifically includes the endpoints, a and b. When we talk about differentiability here, things become slightly more complex. This is because, at the boundaries of the interval, we cannot approach the point from both sides. For instance, at the very start of the interval, there is no function existing to the left of that point to compare it with. Therefore, we have a specific definition for this. A function f is said to be differentiable on a closed interval from a to b if it satisfies 3 distinct conditions. The first condition is the one we just learned in the previous slide. The function must be differentiable at every single point within the open interval, from a to b. The second condition focuses on the left endpoint, where x equals a. Since we cannot approach from the left, we only require that the right-hand derivative exists. Mathematically, the derivative of f at a from the right is defined as the limit as h approaches 0 from the positive side of the expression, f of a plus h minus f of a, all divided by h. Finally, the third condition focuses on the right endpoint, where x equals b. Here, we only require that the left-hand derivative exists. This is defined as the limit as h approaches 0 from the negative side of the expression, f of b plus h minus f of b, all divided by h. In the next slide, we will discuss exactly why this distinction between the left and right limits is necessary at the boundaries. Why this distinction? Now, you might be wondering why we treat the endpoints of a closed interval differently than the points in the middle. Let's clarify the reasoning behind this. First, consider the left endpoint, where x equals a in a closed interval starting at a. The function is not defined for any values of x less than a because there is no left side to the function at this boundary. It is mathematically impossible to check the limit from the left. Therefore, to determine if the function is differentiable at this starting point, we only require the derivative to exist as we move into the interval from the right. This is why we specifically look for the right-hand derivative. Similarly, when we reach the right endpoint, where x equals b, we encounter the same situation in reverse. Since the function is not defined for values of x greater than b, we only check the limit as we approach the point from the left. By focusing only on the direction that stays within the interval, we can formally define differentiability even at the very edges of our range. To help you visualize this concept more intuitively, let's move on to a real-world analogy. 3. Real-world analogy: the smooth road. Now, to help you visualize the formal definitions we just discussed regarding open and closed intervals, let's use a real-world analogy. Imagine you are driving a car along a road. In this scenario, the position of your car over time can be represented by a function, f of t. When we speak about differentiability over an interval, it is essentially like saying that the road is smooth for the entire duration of your trip. To put this in perspective, if the road has a sudden, sharp kink, such as a jagged corner or a complete break, like a bridge collapse, the function would not be differentiable at that specific point because the smoothness is interrupted. If the road remains perfectly smooth from the exact moment you start your journey, at time t equals a, all the way until the moment you stop, at time t equals b, then we can say the position function is differentiable over the closed interval from a to b. This ties back to our previous discussion on boundaries. The start and stop points are our endpoints. Here, we only care about the direction of travel as we move forward from the start and as we arrive at the end. With this conceptual understanding of smoothness in place, let's move forward and apply these rules to a concrete mathematical example. For step-by-step example. Now that we have covered the theoretical definitions and the road analogy, let us apply these concepts to a concrete example. We will examine the function f of x equals x squared over the closed interval from 1 to 3. As we discussed in the previous slides, verifying differentiability over a closed interval requires us to satisfy 3 specific conditions. Our first step is to check the open interval, which consists of all values between 1 and 3, excluding the endpoints. To do this, we first find the general derivative of the function. By applying the power rule, the derivative of f of x, which we write as f prime of x, is the derivative with respect to x of x squared, which equals 2x. We can see that the resulting expression, 2x, is defined for all real numbers. Consequently, it is certainly defined for every value of x within our open interval from 1 to 3. Because the derivative exists and is finite at every single point in this range, we can conclude that the function f is differentiable on the open interval from 1 to 3. This completes the first requirement. In the following slides, we will proceed to verify the conditions at the 2 endpoints. Step-by-step example continued. Now that we have established that the function is differentiable within the open interval, we must proceed to the second condition for differentiability over a closed interval. Step 2 requires us to check the right-hand derivative at the left endpoint, which in this specific example is x equals 1. To do this, we apply the formal definition of the right-hand derivative. We look for the limit as h approaches 0 from the right of the expression. The quantity 1 plus h squared minus 1 squared, all divided by h. Starting with the simplification, we expand the squared term in the numerator. This gives us the limit as h approaches 0 from the right of 1 plus 2h plus h squared minus 1, all over h. Continuing with the simplification, the positive 1 and negative 1 cancel each other out, leaving us with 2h plus h squared over h. We can then divide both terms in the numerator by h, which simplifies the expression to the limit as h approaches 0 from the right of 2 plus h as h tends toward 0. The value of this limit is simply 2. Because we have arrived at a specific real number, we can conclude that the right-hand derivative exists and is finite. Having verified the left endpoint, We will now move to the next slide to perform a similar check for the right endpoint of our interval. Step-by-step example continued. Now that we have verified the differentiability of the open interval and the right-hand derivative at the starting point, we move to step 3, which is to check the left-hand derivative at the right endpoint, x equals 3. To do this, we apply the formal definition of the left-hand derivative. We look at the limit as h approaches 0 from the left of the expression. The quantity 3 plus h squared minus 3 squared, all divided by h. Let us simplify this expression. First, we expand the squared term, which gives us 9 plus 6h plus h squared. When we subtract 3 squared, which is 9, we are left with the limit as h approaches 0 from the left of 9 plus 6h plus h squared minus 9, all over h. Continuing with the simplification, the positive 9 and negative 9 cancel each other out. This leaves us with 6h plus h squared divided by h. By dividing both terms in the numerator by h, the expression simplifies to the limit as h approaches 0 from the left of 6 plus h as h tends toward 0. The final value is 6. Because we have arrived at a specific real number, we can confirm that the left-hand derivative exists and is finite. Conclusion. Now that we have completed our 3-step verification process, we can reach a final conclusion for this example. Since we have successfully met all 3 conditions, namely, the differentiability on the open interval, the existence of the right-hand derivative at the left endpoint, and the existence of the left-hand derivative at the right endpoint, we can confidently state that the function f of x equals x squared is differentiable over the closed interval from 1 to 3. 5 common mistakes. Now that we have walked through a concrete example, let us discuss some common pitfalls to avoid when determining differentiability over an interval. First, a very frequent misconception is assuming that continuity implies differentiability. Many students believe that if a function is continuous over the closed interval from a to b, it must automatically be differentiable. However, this is incorrect. For instance, consider the function f of x equals the absolute value of x. While this function is continuous on the closed interval from -1 to 1, it possesses a sharp corner at x equals 0. Because the derivative does not exist at that specific point, the function is not differentiable over the entire interval. Next, be careful not to ignore the endpoints. When you're tasked with checking differentiability over a closed interval from a to b, beginners often make the mistake of only finding the general derivative formula and assuming that is sufficient. As we demonstrated in our previous step-by-step example with x squared, you must formally verify the right-hand derivative at the left endpoint, a, and the left-hand derivative at the right endpoint, b. Finally, ensure you do not confuse open and closed intervals. To recap our earlier definitions, if you are dealing with an open interval, denoted by parentheses from a to b, you do not need to check the endpoints. However, for a closed interval, denoted by square brackets from a to b, verifying the endpoints is mandatory. Keeping these distinctions in mind will ensure your analysis is rigorous before we move on to the final key takeaways. 6 key takeaways. To wrap everything up, let us go over the key takeaways from this lesson to ensure you have a solid grasp of the concepts. First, regarding the open interval, denoted as a comma b, a function is considered differentiable if the derivative, f prime of x, exists for every single value of x within that interval. As we discussed earlier, this means there are no breaks or sharp corners anywhere between those 2 points. Next, for a closed interval, denoted as square brackets a comma b, the criteria are more comprehensive. As we demonstrated in our step-by-step example with x squared, the function must satisfy 3 conditions. It must be differentiable on the open interval, it must have a finite right-hand derivative at x equals a, and it must have a finite left-hand derivative at x equals b. This ensures the function is smooth not only in the middle, but also as it starts and ends. Finally, please keep in mind the fundamental requirement regarding continuity. Differentiability over an interval is a stronger condition than continuity. In simple terms, for a function to be differentiable, it must first be continuous. However, being continuous does not automatically make a function differentiable. Just remember the example of the absolute value of x that we mentioned in the common mistakes section. It is a continuous line, but that sharp kink at the origin prevents it from being differentiable over an interval that includes 0.